Okay, now we're going to look at chapter 4.1, question 2. And in this question, we've got 3 different circuits, but there are a couple of things that are the same. In each of these circuits, the battery in each of these circuits is identical, and even though each circuit has a different resistor arrangement, the resistors are in fact identical. Okay, so let's label these circuits, the parts of the circuits, to reinforce the idea of what's the same and what's not. So because each of these batteries is the same, they'll have the same voltage, and so let's call that voltage V. Now we'll call it E. So E, E, and E. They all have the same voltage. This resistor will have a resistance of R. Both of these will have a resistance of R, and so will both of these. Okay, so that's our arrangement. Now the questions that relate to question 2 are, which of these resistors has the highest current flowing through it? Which one has the lowest current flowing through it? And which one has the greatest power dissipated through it? In other words, which one is going to heat up the most? So I'm going to show you how we can use a very similar technique that we used in question 1, which is using algebra to answer this question. Before we do that though, let's look at the basics of these circuits and make sure that we understand just the general aspects of how these circuits work. So let's go to a different colour. Now remember, this is the battery, and this tells us how much energy each coulomb of charge is given as it comes out of the battery. So the current is going to flow from positive around the circuit to negative. So the current's going to go this way, like this. That'll be our current. That's the direction of our current. Likewise, the current direction will be like that in this one. And in this particular circuit, the current will come out of the battery, but there's a branch in the pathway, or there's a branch in the circuit. So some current will go this way, and some current will go this way. So that's what's happening with the currents. Now, one thing I need to make sure you're clear on is that just because the currents are going in the same direction, and just because they all have the same value resistors in them, the currents won't be the same necessarily because the arrangements are different. Okay, so that's what the current is doing. Now, these first 2 circuits are in fact series circuits. So this is a series circuit. Well, it has to be because it's only got one resistor. This one is a series circuit because the 2 resistors are one after the other in the same branch. There are no separate branches, it's one single circuit. So this is also a series circuit. On the other hand, this circuit contains a branch, and the 2 resistors are on different branches. This is a parallel circuit. Alright, now a few golden rules to remember about each of these types of circuits. Firstly, in series circuits, the total resistance is simply equal to the addition of whatever resistors are in that circuit. So here the total resistance of the circuit will be R, here it will be R plus R again. The formula to work out the total resistance in parallel circuits is 1 over RT equals 1 over R1 plus 1 over R2. Okay. We'll call that R1, R2, and call that 1R, 1, 2. And actually the book names them, it actually gives them, each of them a separate number, and we'll do that now so we don't create any confusion. So that's resistor 1, resistor 2, resistor 3, resistor 4, and resistor 5. Okay. Now, the next thing we need to be clear on is how the current behaves in each of these circuits. In a series circuit, because all the current is flowing in one single loop, in both of these first two circuits, the current is all flowing through one loop. There are no branches in the circuit. So clearly, in circuit 1, or circuit A, all the current coming out of the battery must all flow through resistor 1, the resistor in that circuit. In circuit B, all the current coming out of the battery must flow through R1 and R2. So that tells us whatever the current that's flowing through R1 is, that must be the same as the current flowing through R2. So here the currents must be the same. So in this circuit, current flowing through R1 will equal the current flowing through R2, which will equal the current coming out of the battery. In circuit C, this is a parallel circuit, and whatever current is coming out of the battery, that will not equal the current flowing through each of these resistors. So if we imagine that, say, 2 amps of current was coming out of the battery, and both of these resistors are the same, then they're going to offer the same resistance to the current. In other words, the current's going to find it just as difficult to go through the R1 branch as it will through the R2 branch. So that means the current's going to split up evenly, which tells us that half of the current coming out of the battery will go through R1, and the other half of the current will go through R2. So whatever current is flowing through R1 in this circuit, that will be the same in this case as R2, but both of those currents will add up to the current coming out of the battery. And when these currents recombine at this point here, whatever the current coming out of the battery is, that will be the same current that's going back into the battery. So we need to be aware how the currents behave. The final thing we need to be aware of before we can do this problem is how voltages behave. Remember, when you are looking at the voltages around a circuit, think of it as you've been given some money to spend at an amusement park, and you have to follow a particular circuit. And whatever circuit you follow, you must spend all of your money by the time you come back to your starting point. So if these batteries were all, say, 9-volt batteries, no, actually we'll make them 12-volt batteries. So let's imagine each of these is a 12-volt battery. Then each coulomb of charge coming out of the battery is being given 12 joules. It will spend that 12 joules passing through this one and only resistor, so by the time it comes out the other side, it'll have no joules left and return to the battery. So therefore, the voltage across that resistor will be the same as the battery, 12 volts. In this particular scenario, scenario B, if each coulomb is given 12 joules, and you're going to go on 2 rides, or you're going to go through 2 resistors, and the 2 rides are the same, which means that the cost of admission for each of those will be the same, which means the same energy payment must be made at each of those resistors. So in other words, if each coulomb is being given 12 joules coming out of the battery, it'll have to spend 6 joules getting through this one and 6 joules getting through the second resistor. So by the time it passes the second resistor, it will be at 0. So that means that the voltage across R1 will be half of the voltage coming out of the battery, and the voltage across R2 will also be half. So if this was 12 volts coming out of the battery, then the potential difference across R1 would be 6 volts. The potential across R2 would also be 6 volts, adding up to a total of 12 volts, which is the voltage of the battery. In parallel circuits, it's different. We can think of a parallel circuit as two separate loops. Now, if this was going back to our amusement park ride again, if you have to follow like a yellow line around the park and you reach a fork in the yellow line, you can't go both ways. You can only go one of those directions, so you have to commit. Do you go through this branch or do you go through that branch? Which means any given coulomb of charge or any given electron or charge can only go through one of the resistors. Half of the coulombs or half of the charge will go through R1, the other half will go through R2 in this case. But each coulomb of charge will only pass through one resistor. And remember, it must spend all of the energy it's got by the time it gets back to the starting point. So if it's a 12-volt battery, then each coulomb of charge that goes through R1 will have to spend all of its energy to get through that one single resistor. So it will actually be 12 volts across R1. On the other hand, those charges that went the other path through R2, because they too will only go through one resistor, they must also spend all of their energy to get through that one and only resistor. So therefore the potential difference across R2 will also be 12 volts. And in parallel circuits, the voltage drop across resistors in parallel will always be the same as each other. Okay, so now let's get into the problem. So we'll make some room. We'll clear this. Okay, so what's the question asking? Which resistor has the highest current, which one has the lowest current, and which one has the highest power? So let's work out the current travelling through each resistor. Pardon me. Now, I'm going to use the algebraic method. Some of you may prefer to substitute values for your voltage. For example, make each voltage 6 volts. And substitute a value for your resistance. You might decide that each resistor is 2 ohms. And that would be one way to do it if you felt uncomfortable with algebra. But it is a good skill to develop. A good skill to develop is to actually use algebra to solve these. So I'm going to use that method and show you how it's done. And it is very similar to the one that we did in question 1. Okay, so let's now try to work out an expression for the current through each of the 5 resistors in this diagram. Okay, starting with this first resistor, resistor 1. Well, let's just call that current I. Okay, the current coming out of that battery, we'll call that I. So through R1, through this resistor here, we'll call that number 1. Through R number 1, we let the current equal I. And in fact, that will equal the current coming out of the battery, which is V over R, or E over R in this case. So there's the expression for the current. The voltage of the battery divided by the total resistance of this circuit, E over R, which is I. Now, if you're not sure what law I'm using, of course, I'm using Ohm's law, V equals IR, and therefore I equals V over R. And I was using well, it doesn't actually, because it's only one resistor, the local version is the same as the global version. But that's the rule that I'm using. Okay, let's have a look at these 2 resistors in circuit B. Now, the current flowing through the circuit is equal to, the current coming out of the battery is equal to the voltage of the battery, which is E, divided by the total resistance of the circuit. But guess what? There are now 2 resistors in this circuit compared to the circuit A, which only had one. And because they're in series, the total resistance is going to be both of these resistors added together. But because they're identical resistors, we can simply say that the total resistance is 2R. So that will be over 2R. So if we now compare both of these first two circuits, we can say that the current coming out of the battery in each case is different. This one over here, circuit B, the current is half the current that's coming out of the battery in circuit A, even though the batteries are identical. And that's because of the effect of the resistance. Now, but the question was, what is the current flowing through the actual individual resistors? But remember, because these two resistors, number 2 and number 3, are in series, then whatever current is flowing through R1, or this resistor here, is the same as the current flowing through this resistor, which is the same as the current coming out of the battery. So the current flowing through both of these resistors is both E over 2R. So resistors number 2 and resistor number 3 both have the same current flowing through them, and that is E over 2R, which is half of the value of this current. So far, the current flowing through this resistor is winning. Let's have a look at the final two resistors in our parallel circuit. Now once again, the current coming out of the battery is going to equal E over the total resistance. But hang on, these aren't in series, they're in parallel. So we need to work out an expression for the total resistance using our parallel resistance formula. So let's go ahead and do that. 1 over RT equals 1 over R1 plus 1 over R2. Now remember, the resistors are the same. So R1 is the same as R2. So I can rewrite that as simply 1 over R1 plus 1 over R1 again. So it's like a third plus another third, which is 2/3. So that actually equals 2 over R1. Now, therefore, 1 over RT equals 2 over R1. So therefore, RT over 1 will equal R1 over 2, or R over 2. So therefore, what we're now saying is the total resistance of this circuit, the total resistance is actually half the value of any of the individual resistors. So placing resistors in parallel looks like it has the effect of reducing the total resistance of our circuit. And that's exactly what happens. The more branches I put in here with resistors, that would actually effectively reduce the total resistance of the circuit. Okay, so if I now just rub this out, so now I can say that in this final circuit, the current flowing out of the battery, current coming out of the battery, will equal E over R over 2. Now, we're going to use state change flip here, so it's going to be E. It's E divided by R over 2, which is the same as stay, change, flip, so it's actually 2E over R. That's the current coming out of the battery. So 2E over R is coming out of this battery. That's the current. Out of this battery, it's actually E over 2R. And here, coming out of this battery, it's E over R. So let's compare those three figures. They're the ones coming out of the batteries. Clearly, the greatest current is the current coming out of the battery in circuit C, 2E over R. The least current coming out of the battery is E over 2R, which is in circuit B. So finally, let's work out the currents flowing through these final two resistors in parallel. Well, remember, if current is coming out of the battery and it reaches a junction, and the two junctions have the same resistance, then the current will split exactly in half. So half the current will go this way, half will go that way. So a half of 2E over R is E over R. So the current going through resistor number 4 will be E over R, and it will be E over R through resistor 5. So resistor number 4 and resistor number 5 the current going through each of those resistors will be E over R. So to answer the question, which resistor or resistors has the highest current flowing through it? Well, we can see that resistor 1, resistor 4 and resistor 5 all have the same current flowing through them, which is E over R, or the voltage of the battery divided by the value of each of those resistors. Part B, which resistor has the lowest current flowing through it? Well, clearly they are resistors 2 and 3. They have the smallest current flowing through them. The last question is, which resistor or resistors has the highest power? Okay, now remember the power of a resistor, or how quickly energy is changed from electrical potential energy into heat and light, is equal to the voltage across the resistor multiplied by the current through the resistor. So we're going to use now the local version of the power formula, because we're looking at individual components. Now remember, the power dissipated across the actual component is the voltage, or the potential difference across the component, multiplied by the current going through the component. Okay, so we'll change colour just so that we're clear on this. And for circuit number 1, or resistor number 1 I should say, the power will equal the voltage across the resistor multiplied by the current through it. Well, the voltage across the resistor, because all of the energy is spent across that one single resistor, the voltage across that resistor will be the same as the voltage of the battery, which is E. So it will be E, and the value of the current flowing through that resistor is E over R. So it will be E times E over R, which is E squared over R. Okay. Now, over here, in this second circuit, the current is half of that in the first circuit. So over here, the power through this resistor here and this resistor here, they'll be the same because those resistors are the same and they're in series. So the power through R2 will equal the voltage across R2. Now, remember, because you've got two resistors in series and they're both the same, only half of the voltage of the battery will be given up across the first resistor and the other half across the second resistor. So the voltage or the potential difference across each of these resistors will only be half of the battery voltage. So the voltage across R1, for example, it will be E over 2, because half is spent going across that resistor and the other half is going across that resistor. So it's going to be, the voltage is going to be E over 2, that's the voltage across each of those resistors, multiplied by the current. Now remember, we said the current is half the current in this one, so it's actually E over 2R, so it's going to be times E over 2R. Now if we work that out, it's going to be E squared over 4R. So clearly, if we compare this one and this one, that is the power being dissipated by each of the resistors in circuit B. Much less, 4 times less than the power dissipated in the first circuit. Now, finally, the power dissipated through each of these resistors, R1 and R2, 4 and 5, I beg your pardon, they'll be the same. So let's do the calculation for R4. So the power dissipated across that resistor will be the voltage across it. Now remember we said, because each coulomb only gets to go through one resistor before it returns to the battery, it must spend all of its energy passing through that single resistor. So the entire voltage will be expressed across that single resistor, which is E. So the voltage across R4 or R5 will be E, the battery voltage. The current through each of those resistors, remember, was the same as the current through the first circuit, which is E over R. So that will equal E squared over R. So what we can now conclude is that if we now look at each of these values here and compare them, then the power dissipated through each of these resistors, this resistor is E squared on R, each of these resistors is E squared over 4R, and each of these resistors is also E squared over R, the same as circuit A. So this resistor, and this resistor are all converting electrical energy into heat and light at a rate of E squared over R joules per second. On the other hand, these resistors are each dissipating electrical potential energy or converting it into heat and light at a rate of E squared over 4R joules per second, or watts. So these will actually be glowing or have 4 times less power than each of these other 3 resistors. So the final answer to the question, which resistors has the highest power dissipated through it, well, that will be the yellow resistors there, and there. So that concludes our answer to question 2. Thank you.